Welcome at the research track, the morning program. Are you all well? We had enough time for a coffee, and lunch will last a little bit longer, so then you can really make sure you meet up with some new people. Carlo, maybe I can give you the floor just for a very brief and short introduction on this first part of the research track. We will have some candidates, PhD candidates later on, some nice presentations, but just give us some words to start.
Thank you. Thanks again, and thanks again for showing up again. I thank you for that again before, but yeah, it's good. We had to split a little bit because we always had our EASI summit. You know, that was the third one. Most of them have been digital. So we're lucky to have a live summit again, but then we're also quietly involved with Brainport, and they also wanted to have a summit, but then you have people doing startups, and there's a lot of other stuff in AI as well, some experts, and if you take them into the depth, then it's not the most interesting for a lot of people. But if you just stay on the surface and talk about startups and how to get money for that, that's not of interest of research people. So luckily we found this way in order to splitting. We get the biggest hole because most people chose for the research track. So glad to have you all here. So we won, yeah. But this is where the ideas have to come up, hopefully. So we were talking about this human and technology cooperation, and when I was listening there, I reminded the story that you might have seen of Steve Jobs once, and still alive? Oh, still alive. Yeah. Steve Jobs once told a story, and you might have seen this once, and he calls it about computers and how this role with human beings is. He called it the bicycle of our mind. I don't know if you remind this. And it was based on a story that he once has seen in a book. And I asked to put off this slide because it popped up in my mind. It's about this one. This is a guy, Wilson, on the Scientific American in 1973. Steve Jobs, when he was relatively young back then, he saw this story on human beings, on actually the entire animal species, and what the body weight is. That's on this axis, and that's how much the cost of transport. So how many energy does it cost in order to move? And you see that the salmon is quite impressive, and the sheep, and man is somewhere in the middle there. Not too impressive for the crown of evolution, you know? This is not a big showing here. So we are somewhere there in the middle, between the dogs and the cows and the horses, etc. Now the horses quite well, therefore we use them for transportation. But then all of a sudden he noted that all down there is the man on the bicycle. So that's what actually said what differentiates us human beings from other species, that we can build tools to perform much better than any other animal. So, man on a bike, and yes, we're in the Netherlands, so let's make some advertisement for that one. So, us combined with machines are beating all other species. That's what actually at a certain moment in evolution made us go further. And he said exactly what's now happening with machines and computers. He called them the bicycles of our minds. We are not that clever as human beings on ourselves, but because we are able to invent machines, we can beat all other ones. And that's what we're going to talk about. How we're going to develop these bicycle of the minds in AI. How we're going to use this artificial intelligence to strengthen our genuine intelligence. And for that we need new ideas. We know how to fight funding. That's not the problem. The progress of the future of development is often claimed is not so much if we have enough technical possibilities. There are sheer endless. Also not the funding, and yes, we would like to join up with you to find these funding, but there are also loads of funding coming up from Europe, etc. That's also where we try to find you in order to come up with new ideas. No, it's the number of people that you can find in order to develop the ideas. And there are quite a bunch of these kind of people here at this moment together. So that's, again, I hope that sparks some new ideas. Most of the presentations that you will see now, of all of them, actually is a combination of people from the university and people out of companies to show how they jointly made this extra step. It's also typical for our university. We do relatively very well in cooperation with on a worldwide scale, by the way. We're always in the top 3, sometimes number 1 in the cooperation with businesses. So therefore, we chose this combination. Hopefully you get inspired, come up with questions, use the breaks as good as possible in order to come up with new ideas, and then we jointly can make proposals and make sure that in 5 to 10 years, everything that happens here will improve your lives. Thanks in advance for that.
Thank
and
you,
now
Carlo.
leave you in the capable hands of Simone again to guide you through this session. Thank you very much.
Thank you very much, Carlo. This was a very, take the mic with you. We are going to start immediately with the duo talk on high-tech systems. Douniel, you were already on stage. Please take your spot again, Chief of Staff, Global Field Operations from ASML. Welcome. Yeah, wonderful to have you here. And you will perform a duo talk presentation with Willem van Jaarsveld, who will meet in a moment. So, yes. Floor is yours. Take it.
Thank you. So welcome everyone. Thank you for attending our presentation. Willem and I will present some work that we've been doing over the last few years. And actually to build a bit on what you described, Marco, with the bicycle, right? We also need a bit of fuel, right? And all this project started at a coffee machine, actually, which is quite interesting. That's the other full of fuel of the brain that you need, besides AI. And actually we're the coffee machine, and Willem was very passionate and was explaining me what he was working on and what idea a bit he had. And that's a little bit how we went on thinking, okay, now how can we apply this to real world? And that's how we started many years ago with a master's student, and all of this project grew to what it is today, to a full-blown research project, consortium with 12 companies. So again, compliments to you, Willem, for starting this so many years ago. Right, to dare to go on the route of deep reinforcement learning with stochasticity included to it, which is not a small endeavor. So I'll go a little bit now to explain to you why we believe from the start it could be applied in practice, and then I'll hand over to Willem to explain more the ins and outs of the model itself and the results. Sorry, can I have the slides on the screen here, please? Thank you. So, as mentioned, I worked at ASML. ASML, we develop, manufacture, we sell, and then we service machines that are used for the manufacturing of microchips. Most of you might have heard of our company already. There's also a nice documentary on the Dutch TV, which is now in English on YouTube, in case you don't speak Dutch. It's also very nice. And what you see really is that we make these very complex machines. Now you have the example of the EUV machine, one of the latest technologies. And these machines are then used by our customers in clean room environment to manufacture microchips. These machines are used as part of a very complete manufacturing process. It's just one of the steps, but it is the most critical. And in terms of production planning, it is actually the bottleneck in the manufacturing process, hence the importance when you talk about uptime. As you might have heard, the chip industry has faced quite some challenges over the last 2 years or so with the supply of chips, with the capacity. Basically, really started with COVID and everybody working from home and getting more demand for devices, everybody working remotely, plus all the other global trends that we knew of before. And you see that the whole industry now, the shortages that we've had have had some real life implications. You see that these are very recent articles that have been published in the last just couple of weeks with Volvo and Toyota reducing their output forecast again for next year because of the lack of chip. I think we're talking about 500,000 less cars for Toyota, for example, and their share value decreased by about 10% on that announcement. But we also have the healthcare business that has been very impacted. And some of you might be from Philips or might be aware with this news article. Medtronic also have been suffering, and in general you see that many patients don't have access to the care they need because the equipments are not there necessarily in the hospitals. The car industry might seem a little bit more remote, but this one has a lasting impact because you see that this 2-year backlog in the car industry has actually some consequences on our CO2 emission objective by 2030. And this is an article of a few months ago already now, but still relevant because we will not be able to really catch up. And the fact that we are delaying the switch over to more sustainable mode of transportation will have also consequences on greenhouse gases and global warming. So this is something that the whole industry really feel the need to do something about and to resolve as soon as possible. And that's the reason why at ASML we service these machines, and we have a very advanced network of warehouses and field engineers to service all these machines. And as mentioned, you see that our customers use the machines a very complex process. So in numbers, to give you a little bit of a feel of what we're dealing with, our machines have a very low failure rate, but we have quite a large install base if you look for this type of assets, at least, in high-tech assets. We're talking about here to service them about 3,000 systems worldwide, split on around over 45 locations. And more importantly, we have about 10,000 service parts that we use to be able to service the systems and to guarantee some uptime. Why do we need this uptime? Because obviously there is a high cost impact when the machine is not functioning at the customer. 72,000 euro per hour. That was a number that we used to use a few years ago. We don't have a newer number, but that gives you already a range. Whether it's 72 or 80 or 100, it is an impressive number. What is more interesting actually in this case now is that to really have an impact to help the whole semiconductor industry, it's also the next step about reducing the variation in how the uptime is delivered. And then you see that when the machine is down at the customer for 24 hours, it takes about a month for customers to recover their production, for their work in progress inventory to get back to normal, and for their shipments to their own customers to get back on track. And for that reason, we really gear up on our service supply chain to make sure that our customers can make the most out of the asset to try to decrease the impact of the chip shortage. To do that in a proper way, many decisions have to be taken, as many of you are probably aware of. Some of them on strategic level, but also on tactical and operational. So I put a little bit of quite a summary because some of you might be more on AI expertise, so I wanted to put this on the screen to make sure we are also aligned before Willem takes the stage. And you see that many decisions need to be taken on strategic level. We need to decide on how we want the network to be in place to service the customer in the right way, but also what type of services do we want to deliver. Once that is done, you can go into deciding how will you plan for your materials, are you going to plan for your engineers, what will be your repair strategy for the return flow, also taking into account circular economy and all the sustainability objectives that we follow. And then on operational level, that's something that takes place on a not even daily basis, but every single minute that we talk about, because we run 24/7, you need to decide at one point when you have one part, where should it be shipped? If you have a tool, where should it be shipped? Where should the next service engineer go? To which customer, to which machine? And which part to repair first in that backlog? Now the challenge is, like many other companies, we have been also suffering from some supply chain challenges, right? So we understand a bit more between the geopolitical tensions, but also because of the rising prices of fuel and the war in Ukraine and so on, you have a lot of supply chain disruptions. And that is the reason why we focus ourselves on the operational level, because this is really where we felt we could have the biggest impact with our deep reinforcement learning model. And this is also what Forbes calls it, indeed, to drive for more innovation in order to make better decisions every day to compensate from the fact that there are disruptions every day in our supply chains today. Can I invite Willem to the stage?
Yes, thank you, Douniel. So indeed, we are going to talk about spare parts decision making, spare parts planning, and we're going to focus on operational decision making. So I've been working on spare parts sort of optimization problems for more than 10 years, and then I think within sort of spare parts operational decision making is actually much harder than say tactical decision making, at least in a sort of computer science sense. And the reason is if you have sort of a tactical decision, sort of setting, for instance, the inventory levels in your system, or making some other plan, and this is a plan that you can evaluate. So there is, say, some solution space, and you want to optimize that, and this plan, and then you typically make some objective function, and then you're looking for a plan that satisfies this objective function, but it's one decision, right? If you think about operational decisions, there are many operational decisions, and they are sequential. And every decision you make is typically also followed by new information that you get. So you're constantly subject to uncertainty, and you're making a few decisions, and then new uncertainty and more decisions. And the difficulty with that is that if you make a single decision, then that decision is going to impact the future. And then you want to actually take into account what you would do in that future if certain things happen. So to make this single decision, you actually need to consider all possible, say, futures that could happen and all the decisions that you would make in those futures. And that is, well, that is quickly getting very big. So theoretically, yeah, that brings you in what people call the P-space complexity class. And that's sort of a class which contains even more difficult problems than NP-complete problems that maybe some of you are aware of that class. Also sort of in my field, which is sort of optimization of logistics, sort of this operational decision is considered, or at least was considered, to be maybe intractable. It's really very hard to do a good job there. So personally, I was very excited when I saw this paper and these results. So this was a company, DeepMind in London, that did this. They were later acquired by Google. And they actually, well, through a combination of very clever software engineering, some algorithmic advances, and well, a lot of clever combinations of ideas, they came up with a relatively simple algorithm. If you read the paper, there's, well, it's fairly manageable. And then they were able to really do this. So they could have a game where they need to make a single move, but while they were doing that move, they were considering all the future moves that the opponent might make and what they might do then, etc., etc. And they really sort of make a quantum leap to solve these problems. So as said, I was super excited about that, and also sort of a lot of the developments underlying this were also underlying sort of the logistics optimization field. So I started working on that, and indeed I got some nice results. And this was when sort of the coffee break moment happened, where we decided that, hey, yeah, if this might really work, then we have to really try it, right? So that's what we did. And this was a master thesis internship of Valentijn at ASML. And what we did for this thesis was we took just an out-of-the-box, say, reinforcement learning algorithm, and we were curious, well, how well it would perform. So what we did also is we took a problem, an allocation problem that is very well studied within ASML, and we took a model for that. And we used that to build a model for evaluating how well, say, our agent did. And that same model also underlies sort of a set of clever, say, engineered heuristics, not AI heuristics, but regular heuristics that you could also test. And we could beat that benchmark, even though that benchmark was specifically designed for the model on which we tested it. So that was arguably a good proof of concept, but it was no more than a proof of concept, because to make this DRL work, we had to scale down the problem. And so Douniel sketched how big this challenge is at ASML, thousands of spare parts, many locations. We had to scale that down to a handful of parts and a handful of locations. So if something works sort of in theory but not yet in practice, then you have to push really hard to get it done. And most of that is actually engineering. So I'm not sort of a fundamental AI researcher. I'm not pushing for sort of general intelligence or anything. I'm just happy if I can solve one specific important problem well. And I think the push that we are now making is we are looking at this class of sort of allocation problems. And we are sort of investigating what would be needed to scale these type of algorithms to those big problems. So that means we use anything we have. So if we know that this problem has certain characteristics, then we are happy to build an algorithm specifically to tackle those characteristics, meaning that it probably won't work well for, say, playing Atari games anymore. But we don't care. We just want to solve this problem. So we are developing sort of this framework that is specifically aimed at these problems, with also funding from a Dialogue funded project. And well, we have accomplished some things so far. So this sort of official project started maybe a bit more than a year ago. So what we've been able to do is we've been able to sort of, these algorithms need to be trained. We've been able to do this training on a supercomputer and then distribute it really over, say, thousands of hardware threads on multiple computers. And this is also sort of a more AlphaZero-like algorithm. So this distribution also goes much better than it would go for, say, a PPO type of algorithm. We have made specific sort of developments to deal with these huge uncertainties in these environments, because you just don't know what will, say, fail next, and you have to anticipate all of that. And that also makes it hard to train, say, AI models on this problem unless you deal with that. We have also been able to scale to like hundreds, or recent results even thousands of SKUs. This is for hundreds of SKUs. But well, there is still also a lot of things that need to be done. So we still have some domain knowledge, some knowledge on this problem that we think we could incorporate, and we haven't gotten to that yet. And yeah, one particular challenge is also you have, on one hand you have many SKUs, and on the other hand you have all these locations. And at this moment we can either do a lot of locations or a lot of SKUs, but both is still a bit of a challenge. But I think we are getting there eventually. So this is some results for what I would call maybe a 0.5 or a 0.8 model, where we could show that for a pretty large problem, that we could have a sizable reduction in costs, and an even more sizable reduction in waiting time. So in sort of, yeah, how this is the 72,000 euros that you would like to reduce as much as possible. So summary. So, well, Douniel told us it's important to use these ASML machines as much as possible. And well, say controlling this huge network is a big challenge, and it involves repeated decision making. And well, repeated decision making is a super difficult problem. We have been seeing some very sort of promising results using reinforcement learning, but to scale it, we need to have very specifically engineered algorithms for these type of problems. And we are starting to show some promising results, and I hope that maybe in some years I will be able to, well, to tell you where this led. So thanks.
Thank you, wonderful, and thank you, Douniel. Wow, this sounds so promising. Pooh. Questions, remarks? Yes, for sure. We have some time, but yes, the gentleman over there. Just. Yeah, well. Yes, please step on stage. I wanted to invite you already. Yes, tell us who you are and what your question is.
Okay, thanks a lot. First of all, enjoyed your session. My name is Satyajit Vatamwar. I'm from Unilever R&D. And my role is data science and digital expertise leader. And my question is going into the same area, but also a little bit with the digital twin side. So I'm wondering, the uncertainties that you mentioned there, naturally they have influence towards optimal decision making by the reinforcement learning algorithms. But then do you make use of the digital twin of your environment so that some of these uncertainties can be simulated?
Digital twins, may they serve to solve the uncertainties in the program, in the research?
So I think within ASML, shall I take the question?
Go ahead.
So I think within ASML...
Yeah, you did, which is fine, which is fine.
Yeah, I should have asked before.
Go ahead.
So I think within ASML there is a lot of expertise in building models. There's at least a decade of expertise in building models that also incorporate sort of this uncertainty and that are at the same time accurate and sort of fed with, say, forecasts or data. And those models are just like a complete model, so you can take actions in those models and you can sort of see how they work out. And sort of the aim of this project is not to improve those models. I think those models are they are very good, and they've also been used for all sorts of decision making at various levels, where they prove to be sort of sufficient. So what we are looking at is really sort of a model-based reinforcement learning, a bit like learning to play chess. So you know the rules, but you still need to learn the game, which is a big challenge by itself.
So in a way, you need to practice.
Yes.
It's not that much. So in that sense of the digital twin. So the models are there and they are at stake. They are okay. But now that's what you're investigating. That's what you're researching. Yeah.
Okay. Thanks.
Other question or remark to? Yes, the gentleman over here.
Yeah.
Just. Yeah. Wow.
My name is Arjen den Boer. I work at VDL. So we are a supplier to ASML. And we are also one of the reasons why you have shortages.
I didn't say anything.
Okay.
So
if you say so. Yeah.
So I was thinking, well, we have to team up, right? We have to work together. And I was thinking, we are at this moment at parts, VDL ETG. We are in transition of our old ERP system, BAAN 4, to Infor-LN. And that takes 1 year, perhaps 2 years. And I want to speed that up in my role as logistic manager for parts. And I was thinking, well, I have perhaps not that a budget, but I have data. So if perhaps and I'm wondering if the university and ASML would be interested.
In your data?
Yes, well, but here it comes. I believe that we have not a good solution for our job shop shadowing problem. It's difficult. We have 50 production cells. We have 3,000 orders, spare parts making for ASML. And if we do not the forecasting right, and if we do not the smart allocation of jobs to specific dual constraint problem, machines and people, we have a bad performance. We have low productivity. We jeopardize your sales. So perhaps it's more for at the coffee break. I'm open to share, on behalf of VDL, all our detailed operational data, and I'm interested if we can work faster than the advanced shadowing tool, which I only get over 1 year, and we start using the chest intelligent learning things and see if it works.
Okay. Now, for
That
sure,
would be my
you
offer.
will have lunch together, that's for sure. But maybe a short, brief answer to
Yeah,
this.
let me answer very fast. I think we can even do things before that, because as Willem mentioned, now this project turned into a consortium, right? Which is supported by TKI Dialog, which means that actually 12 companies are part of it. And any company can, with a master student from Eindhoven, for example, already try to apply some of the learnings from this research.
Yeah.
So that's something we could talk about.
Okay,
Yeah.
thank you.
Okay, wonderful. Well then, thank you so very much that you were with us, sharing this information, this exciting research, and for sure more people will want to have lunch with you, I can imagine. So thank you very much.
All right.
A last applause for the two of them.
Thanks.
Oh, and a little present, see that? And now it is time to meet 3 PhD candidates, and they are from different departments like electrical engineering, industrial design, and also mathematics and computer science. So 3 short research presentations. I think it's the 3 of you here. Yeah, wonderful. We are really curious to find out what you're working at. So we will start with Zaval, Mondragon, video coding and architectures from electrical engineering. Please, go ahead. The pointer is over there if you need it. Yes.
Well, hello everyone, and thanks for the introduction and for the invitation. So I'm going to talk. Oh yeah, good. about the research I've been doing in the past couple of years. So I would like to begin by asking you to think about some of the challenges that, for example, radiologists experience while they are interpreting CT images. So there are actually two very important ones. The first one is that the lesions can be very small, right? Like there can be like a small bleeding, a small tumor present. The other one is that the contrast between the lesion and the actual image or the rest of the parenchyma in the brain is very small. So let's look at an example. So here in the leftmost or the rightmost picture for you, actually, we can see a CT scan slice where we have a small bleeding that is being highlighted, right? Oh, yeah, it's here. So here we can see that this bleeding is very small and very low in contrast. And therefore, we can see that the quality of the image is very critical because if the noise increases, actually can mask this lesion. So here we can see that if we, for example, wanted to reduce the radiation applied to the patient, for example, down to 40%, the amount of noise increases substantially and the visibility of the lesion starts decreasing. And this goes even further. So if, for example, we did 20%, we cannot see the lesion anymore, right? So we can see that it's very critical. And of course, like you could ask, okay, why can't we just keep the radiation dose as it is and then everybody happy, right? And of course, that's a good point. But it can be seen that it's not, this amount of noise present in this image is not exclusive, let's say, to reduce radiation protocols, but can happen, for example, if we have multi-energetic images where we have more than one detector that is sensing or the radiation per detector decreases, or if we have a very thick patient or a sharp kernel that essentially emphasizes this noise, right? So what can actually we do in order to eliminate the noise or to reduce it? Well, there are different solutions, right? So there is iterative reconstruction. There is, so where we are iteratively reconstructing this image, and at every iteration we enforce some property for smoothness or regularity. There is also like optimization-based things like total variation denoising, where we assume that the image is piecewise constant, and we are enforcing some this property also iteratively. And well, of course, these two solutions are very powerful, but they have as a disadvantage that they are actually iterative and they're sequential, which makes them quite slow. Of course, we all know, and we all are here because in the last few years, we have seen that neural networks are playing a bigger and bigger role in signal processing tasks, including, for example, noise reduction. And that's the one we are going to talk about. So specifically a denoising autoencoder, which is actually the simplest of the architectures. And we chose that for something that we'll discuss in a moment. So what exactly a denoising autoencoder is? Well, it's actually very simple, right? It's a task where we have one noise slice, right, that of the CT patient that we are trying to map to a clean slice, right? And in the middle, we have a neural network that is being trained for this task, right? And this autoencoder has two parts, which are actually very simple. So first, we have the encoder, which is mapping an original signal to a multi-channel representation, right? And this encoder is nonlinear. After this multi-channel representation, right, we go to the decoder, which is doing exactly the opposite, right? So we have multi-channel representation, and later it maps it back to the original signal domain. And we reconstruct our image that is already clean, right? And this, in principle, is very simple. But we know that the architecture is actually extremely non-linear, right? We have multiple convolution layers, maybe pooling, etc. And every convolution layer, we have a ReLU, which is basically eliminating pieces of the signal. And of course, we, as some medical application, we would not like to think that maybe this signal will be processed by something that could have a corner case, where we could have some critical failure or introducing some a structure that is not desired, right? So we analyzed this problem, and we thought, like, okay, actually, there is a strong resemblance between the structure of an encoded and decoded network and some things that are actually very well known in the signal processing domain, or in general in image processing applications, which are, for example, the discrete wavelet transform or the discrete cosine transform, which are transformations which we also do some convolution with some kernel. We map to multi-channel representation. Later, we apply some nonlinearity. And in the inverse transformation, we do exactly the same. We do a convolution and sum all the channels, and we recover our signal. So we actually exploited this idea and decided to do some sort of autoencoder based on a similar idea. We're having a linear encoder and decoder and some nonlinearity in the middle. And we actually saw that it works quite well. So here we have two examples, right? We have 2/4 dose CT slices from a public data set. And we process it with, well, like here in this case, it's just a simplified thing, but we process multiple algorithms. In this case, we process with our algorithm. And next to it is a reference, which is called FEP-ConfNet, which is a very popular choice for CT denoising. And of course, here we have the ground truth, which is a full dose CT slice. So we can see that actually where our method is able to eliminate a significant amount of noise and preserve the structure relatively well at the same, or at least equivalently to the reference method that we have here. And of course, like, the question would be like, okay, if you achieve a similar performance to a state-of-the-art network, so what would be the advantage of where we even try to do something different, right? And the reason is that, for example, our model has other advantages, which I think can be very handy for different applications. So the first one is that the model is very small. So it uses about 1% of the parameters of the reference. It's very memory efficient. So we use, I don't know, for training a model of this type on full images, maybe about 2 GB of RAM compared to 10 or 8 of the other model, right? And also the execution time is very small. And of course, like, we are, well, this leads a little bit to the closing part of this presentation. So we, well, I would like to close by saying that, of course, like, this is a very simple problem, relatively, but we would like to use this actually as a platform to understand other problems and the operation of other networks. And that's something that we're already working on, to try to build like some framework where we integrate what we know of signal processing and what we know of neural networks, and we can actually try to explain and interpret better from a signal processing perspective these things. And of course, like, probably will not be in the time of my PhD, but I would like that in the future, for example, when we think about the problem with a neural network, for example, nowadays we don't know which activation or how many feature maps or which pooling, etc. But I would like that in the future, when we actually know something about the problem and something about how the signal is processed, and we can integrate the two to decide or to take these design choices, to lead up to a more efficient and interpretable model. So thank you for your attention. I leave my contact details and, of course, like, the 2 articles that led to this presentation, in case you want to look at them. And, well, thanks so much.
Thank you so much, Luis. Thank you. And please do not downsize it. Do not downsize your research as saying this is a small problem. No, the solutions found and the findings could help us, like you stated at the end. If this platform would be used for others, it is tremendous. So it's a great start, I would say.
Thanks.
Time for one question or remark, or later on during lunch, that's fine as well. It's up to you. Is there one? Not for now. Wow, you did a great job. Well, thank you so very much for having been with us. And then we continue with Peter Lövei from Industrial Design. Beautiful title. Please step forward, Future Every Day. Yes, the floor is yours. You will just take it away, and then we will see what happens. Yeah?
Yes. Welcome. Did you know that data, collection of data, and AI can help changing your lifestyle? Well, of course you did, since you are here today. In the next 7 minutes, I will also talk about why caring for your heart using data matters, and how we here are actually creating a new atrial fibrillation outpatient clinic that shows how it can happen in real-life settings. 1 in every 50 person in this room might actually get diagnosed by atrial fibrillation. It is a disease that is coming up more and more with the aging population. We have heard in the morning about all the healthcare challenges. One of these patients is Ilse. She has recently started to experience a very rapid heartbeat. At the same time, she was very tired, and she got really afraid, like, why could this be happening? So she went to her GP and asked for a diagnosis. Here they have realized that the case is this atrial fibrillation with her heart. She also learned that this can increase her chances for a stroke. And then she realized that that's not so good. She has 3 kids, 67 years old, and still wants to spend time with them, also with the potential grandkids who could be born. But she was also told that it is possible to work on the risk factors that are related to this disease in order to treat it. So she could stop smoking, she can start a more physical activity, and also start to eat better. At the local hospital works Alex, who is a nurse practitioner, and he works really in the cardiology department, and what he is experiencing is that he does not have enough time for patients like Ilse. When they come by, they cannot fully discuss the problems, and also that the care that they are providing is really much focusing on treating atrial fibrillation with an intervention called ablation. So this is really just focused on patients coming in and doing the operation. But recently, by his boss, he was asked to be part of a new outpatient clinic where they will change this. So they will get more time to spend with the patients and give a more personalized treatment. And he was very excited about it. He was already happy that he can then redesign the way care is provided. Well, if all of this sounded like a dream for you, then I have very good news. Because here in the region, we actually set up this new atrial fibrillation care pathway at the Katarina Hospital with the following in mind. So we are providing something that's nurse-led. It is technology supported, and we are really focusing on the risk factors. So first of all, our team went out and explored how the current care is provided, what are the points that we can change, and how data and the systems that they are using can be useful and changed. In my PhD, I'm especially focusing on this, like what data is collected and how we can use it for improving the care. So our solution in the center is a patient engagement platform, which patients can log in and look at the content articles that are focusing on the risk factors that they are facing. So as you can see, when we are following this care pathway, first they are assessed which risk factors are actually present for them. Then they are coming up with a specific treatment, and this is then supported by the patient engagement platform to also learn more on how to work on these. So on top of what I mentioned for our patient, there is also sleep apnea that we are looking into, and also high cholesterol or hypertension. And then at this moment, we are still doing the ablation procedure, but in some cases, the cardiologists and the nurses still evaluate whether it's possible to actually eliminate the ablation. And then we are entering more of a monitoring case. All of this is then, the care is still coordinated. There is data monitoring happening along the way, and this data is shared by the hospital, the academic partner, and also with us as industry. And then all the interactions are also really in the center part. So there are face-to-face consults, telephone consults, but the platform also supports the exchange of chat messages between the patients and the healthcare professionals. And we put a lot of focus into how to create really the care programs that are treating these risk factors. Based on the early incoming data, we are seeing that it's already successful. So the clinical trial was launched last year, December, and we already have 73 patients onboarded from a wide variety of age ranges, and half of them are onboarded in the control group, which does not use the patient engagement platform, and the other half is onboarded with the patient engagement platform. The patients are currently in different phases of the trial. So some are still in the risk factor treatment phase, just before the ablation, but there were already ablation procedures performed, and we are already collecting the afterwards exit questionnaires, where we are looking at how much we have improved the quality of life and the patient experience during this clinical trial. What we are seeing is that the engagement towards the platform and the fact that patients are logging in and reading our coaching items is highly effective. And what I would like to also highlight, just in view of also this morning's presentation, is that this would not be possible without a wide collaboration between academia, industry, and the clinical partners. I would like to thank you for your attention, and I would also like to highlight that atrial fibrillation is not only the one care where this approach could be used. So I'm looking for other kind of care possibilities where such an approach would be possible. Please talk to me in the break. Thank you for your attention.
Great, Peter. Do you have already some fields in your mind where this approach could make sense?
So other heart diseases like heart revalidation clinics would be possible, but also other lifestyle diseases where behavior change is a possibility.
Exactly. Yeah.
Yes.
Did you face privacy issues?
So for this trial, we needed to go through the medical regulatory process of the hospital. But luckily, because we are using a medical software, it was much easier to implement it in the field.
Wow, great, great, great. Wow, inspiring again. Wonderful PhD candidate here on stage with me. Questions, remarks? Does somebody see a field in which this, hey, yeah, why not? Let's be, no, you need a microphone. VDL. You see possibilities everywhere, which is great. You are AI positive, yeah. Not yet.
Not yet.
Just try. Yeah, I guess this is it. Just try to keep it close. Okay. Mm-hmm. Yeah. Okay.
Yes.
Yeah. He really is sharing it with everybody with good ideas.
Thank you.
So, lunch is already given for him, but maybe the network drink later on this afternoon.
Right.
Great, thank you so much. It was wonderful having you here on stage. Thank you very much for sharing these insightful. Luis Perez Rey, from the Mathematics and Computer Science, the Interconnected Resource-Aware Intelligence System. Please tell us all.
Yes, perfect. Already? Yes.
Yes, it does.
Hear myself. Okay, perfect. So, good morning, everybody. Today I will be giving my presentation on my PhD project, which is on 3D model retrieval with disentangled representations and geometrical priors. But for that, I want you to first look at this object I have in my hand and to think whether you can recognize it. I know it's going to be difficult, right? I don't think anybody will see it, but maybe I can help you a bit. I took a picture of it, and here it is. Looks like a pile of dirt, right? So I think still you cannot recognize what it is. Let me help you a bit more. I think now it's clear, right? It's just a small toy from Lego. So for us as humans, it's difficult to identify objects when we see them from difficult orientations, right? And this is no different for machines. So my PhD project is about identifying 3D models within databases that are more similar to a query. So, for example, let's say we have this 3D model, we take some pictures out of it, and then we have a database of other 3D models. So the objective is actually to find which is the most similar to the one I'm providing. So in this case, of course, it would be the other robot. But there are some challenges to it, and also there are some usefulness applications for this. What are some useful applications for this? For example, for designers who want to make a video game, make a movie, they would like to actually retrieve 3D models that they have in mind from large databases in simple ways. But what's the problem with this? How difficult can it be? One problem, for example, is how many pictures do you actually take from the 3D model to identify it? That's the first challenge. So in the first challenge, if you do it naively, take a lot of pictures of it, then take a lot of pictures from the database, compare them. That will be very inefficient. So ideally, we actually want to have a model which just sees a first picture, let's say from a random orientation, and it has already the information of which could be the best next view to actually see in order to identify it. Let's say we see it now from this side. Then in that case, it becomes easier to identify. The second challenge that we actually have is, for example, what does actually similarity mean? That's just very vague. I told you first, yeah, if we have this database, then the robot is actually the most similar. But how about now? Actually, now it could also be because of the color. So it might be that actually the car is the most similar one. Or maybe I'm interested in the background somehow. So actually, this other model is actually the most similar. So this is a problem also about the interpretability. What determines actually similarity between 3D models? So in order to solve these problems and these challenges, we have proposed the following approach. First of all, you have your 3D model, but it contains, and the pictures that you can take from it. But you want to actually extract the important information for your task. So for that, we want to create small data representations for each of the 3D models to make it easy to compare, and also to separate the relevant information that you will need for your task and solving the challenges. So let's say we first try to separate the information about all those perspective things that you can apply to the 3D model when you generate your images. Let's say the lighting conditions, the orientation, also maybe the backgrounds as well. And you want to separate it from the actual information from the 3D model itself. What's its color and what's its shape? Such that it becomes then easier to identify. So how do we do it? We do it, first of all, by learning the transformations into the data representations, which we call symmetries. And the second part is we disentangled all the extra information that we have from the 3D model itself. Let's say in this case, we actually have, for example, several factors that contribute to the identity of this model. Let's say color, let's say also the shape itself. And if we create the data representation, we want to actually be able that if, for example, we're interested now in having the same type of object, let's say airplanes, then they're close together in the representation space. But let's say we change our opinion and actually we're now interested in the color. So the representation space changes accordingly. So in order then to also solve the problem about how can we identify the most informative views, then we use both approaches. We would use the symmetry, the transformations that we have learned in the representations to guide and know which are going to be the next new views that will help us identify actually the 3D model, and then combine it with the extra information that we have already separated from the 3D models themselves. But we're here at the AI Summit, and we are going also to talk about sustainability and vitality. So what about sustainability? So other applications that you can use this kind of approaches that we have developed are, for example, if you want to identify, let's say, an environment or an object using, for example, a drone, then it would be easier if we actually know which transformations the drone has actually to do to actually identify the object in less steps. So you end up using less computation, energy, etc., to actually just identify that this would be the best view or the best position or the best transformation to identify the 3D model. And also, in general, we can do less computations, we can do less memory. So the basic and naive approach, where you render, let's say, 80 images, ends up with having around 2.58 megabytes for a single 3D model. But when you scale it up to actually big databases, and let's keep it moderate, just an available already dataset on which is called Thingiverse, which is just 3D models for printing, then it ends up being like around 25 gigas, which is already not small, but there are even more and bigger databases that are increasing, especially with the inclusion of LiDAR technologies into our mobile devices. With this, I would like to thank you for your attention. I want to also mention that my project is together with Prosus, one company here at High Tech Campus, and that my project is also in the interconnected and resource-aware intelligence systems. So, if any of the following keywords interest you, you can come and talk to me in the lunch. It could be either computer vision, active learning, uncertainty estimation, or just 3D model identification. Thank you.
So, wonderful pitch. The three of you, you are so great in pitching also your research. That is wonderful. And the keywords, do they ring a bell? Because he will be here all day. Please go and talk to him. And team up. Team up, please. That's what we are here for today. Wonderful presentation. Do we have questions for Luis before we go to the final speech before lunch? Because you can take the opportunity, or you can also keep it for later. That is just fine. Yeah, just one question over there. The catch box will come and find your way. Just hold on a sec, Luis, then...
Yes, no problem.
Yep. Choo! Wow. Well done.
Hi, thanks for the nice presentation. I'm Bram Groten, also at the Department of Mathematics and Computer Science, but I'm not very familiar in computer vision yet. Although I have heard of a famous paper called NERV, that also does this 3D modeling, I think.
Yes.
How is your work compared to that, or do you even use that?
Yes, that's a different approach, at least in the sense of their main objective. If I'm not mistaken, NERV is more about rendering, for example, 3D models with limited views. So it can be used in that case for generating, for example, 3D view, more views from a single image. That's one application that I know they can do. So it looks like 3D kind of, but it's mostly, I think, about rendering itself. And my focus is more about getting the models, but it's a very interesting work. I completely agree.
Yeah. Okay, thank you so much. Yeah. Well, thank you, Luis. It was great having you. Wonderful. We will talk about intelligent robotics for haptic interactions, and there you are already. Good, good. Irene Kulling, Assistant Professor, Dynamics and Control, Department of Mechanical Engineering, TU Eindhoven. Wonderful. Take us with you on your journey.
Yes, thank you very much. So before I start, I would like to give you a little warning. There won't be much data in my presentation, and there also won't be much algorithms in there. But what I'm going to show you is a huge field of potential, so that in 5 or 10 years, we could have all these algorithms and all this machine learning for these type of structures. And what I'm talking about is both haptic interactions. So what you heard so far, we mainly use visual input for all kind of models. Why not haptics? And the second thing is soft robotics, and that's about flexible structures, and I will get into more detail throughout my presentation. So let's start with haptics. Not everyone might be familiar with that, but haptics is basically everything that is related to touch. So it's about grasping objects, it's about recognizing objects through touch. How do I know that this is a pointer, where the buttons are? I don't have to look at that, but I can use the information to actually navigate. And you could also think about haptic technology. So that's all type of technology where we use haptics or where we build interfaces to enhance this kind of haptics. And you see 2 examples here at the bottom, and one is a very challenging task, although it looks very straightforward, and that's picking raspberries. So you might know if you try to pick raspberries yourself, once in a while you squeeze some and then everything gets pink. Try to do that with robots. It's almost impossible currently. And the second example is more like a teleoperation kind of system. So you have a human interacting with a human, but you have a robot in between. So you could say it's like a robotic avatar following exactly the movements that you do. So to give an example of that, let's see whether the video plays. So this is kind of state of the art. I mean, there are some different systems as well, but what you see on the right, it's a human operator having a kind of exoskeleton glove and a headset where you can see the video image of that you basically see on the left. And on the left, you see the robot trying to pick up those boxes. And if you see, as soon as the robot has a block, you see that the fingers of the participant are not completely touching each other. So that's the haptic feedback that we give through this glove. So this might look smooth to some of you, but if you think about rehabilitation, this is a task used in rehabilitation, and people can do at least 60 to 80 of those cubes within 1 minute. And actually our best teleoperator user does about 12 to 15. So we're not there yet. And if you look about kind of the clumsiness of grasping those cubes, it really reminds me of this very old study from the 70s by Johansson, a Swedish researcher, who, the task was to light a match, so the woman did that perfectly, but now in the next video, her skin is anesthetized. So that means that the touch receptors are not properly functioning anymore. So she still has the control about the action. She can still have some information about forces from higher up in the body, but she just doesn't feel it. And what you see is that it has this similar kind of clumsiness that we just saw in the other teleoperation video. And in the end, she managed, kind of spoiled it, but she managed. And just as a remark here, with the robot, we won't be even close to picking up matches. It's just way too small now. But that's something where we want to learn from humans and how we do that. And if you look at this remote haptic interaction, then you can think about, okay, what's the type of information that I need to send? So this is a control scheme. So on one hand, you have the operator, then you have some kind of interacting device. Then you have, I now call it controller, but it's like computer, every calculation goes in between. And then you have an environment and a robot that interacts there. And in this case, in this example, as I mentioned, I would like to focus on the human-robot-human interaction. So that could be healthcare applications. In the pandemic times, it would have been great if we would have had this robotic avatar where we could just visit our grandmother within a safe kind of environment. But to actually be able to hand over a cup of tea, or much safer, a bottle of water with a cap on it, we need to know so many details. We need to be able to sense the temperature, the weight balance, all these little details, and that's what most people focus on. It's about the sensing. Well, I would argue that the actuation on the other side is even more important, maybe, because we have a lot of sensors. We can know things about temperature and about weight and all these things, but how do you give that back to a human operator? And this could also apply to working in the metaverse, for example, or having trainings in a virtual environment. We have such nice visual graphics, but we can't feel anything. And yes, that's partly a hardware problem, but also with the existing hardware, I think it's really a challenge in data. What type of data do we need, and how can we combine that? So one of the solutions that we're having is to use soft materials and soft robots. Just as a short introduction on soft robots are typically flexible structures, could be balloon-like, they're deformable, but we of course still would like them to be reliable. And as an example of what happens in nature there, so you see the octopus on top, so the tentacles of an octopus are completely flexible, and still it can grasp very well. Also the trunk of an elephant, there are no bones in the trunk of an elephant, it's all muscles and soft tissue. And what you see is that the elephant can be gentle, it can be very accurately take the banana from the boy. But we also know situations where an elephant can like knock out someone, right? So it's like you have a very wide variety of being strong and gentle. So from this soft robots, some characteristics are safe interaction with humans. You have this multi-purpose flexibility. You know it from your own hands. We're pretty good in a wide variety of tasks. We might not be the best at one specific task, but we can do a lot of things. So there are already different types of grippers or hands being developed, all soft, so based on these tentacles, but also in the lower corner, more on like a how do you call that, meat-eating plant, so that actually closes the leaves. So there is much inspiration in nature that we can actually use for that. Just to point out one more time, it's not going to replace your traditional robot. If you need something to be strong and very precise, don't use a soft robot. However, if you need this versatility, or something that is interaction with delicate objects, and having soft components in there, or a soft robot could be a very good solution. So just very quickly to show some examples on how we can get that into this teleoperation that I mentioned before. So these are some very preliminary prototypes, not very nice, but it gives you an idea. So we can track the fingers of the hand and then have these soft structures move. The second one is a more sophisticated finger already. We have a complete mathematical model and dynamic model of this finger that we can use for simulations, also for making a small digital twin of it. Not very impressive yet, but we're getting there. So this is the same type of fingers with an inverse kinematics model in virtual reality. You see it's much faster now because we don't have the pneumatic delay. The finger is pneumatically actuated. And in simulation we could do already interesting things like having a 4-link robot following a desired trajectory with a desired angle at the trajectory. But then this is all like one way, right? We're sending information and we want to get the feedback back. We want to feel what's going on. So that's where we use examples from virtual reality. So for example, this is a task on a virtual button click. So you see a very basic virtual environment in the top. And then an analysis of a soft silicon cylinder. It looks like this, so the white one. The black one is the mold. The white one is the cylinder itself. That can inflate with pneumatics. And then we can put it on the finger. So the next video will show that much better. Oh, wait, back. Does it play? It doesn't. Could you play the video? Maybe. No? Okay, then it doesn't play. I'll explain what's in there. So you see the soft cylinders on top of the fingers, and then the virtual environment. And so she's wearing the headset. She sees this, and then if she pushes one of these buttons, the cylinder that is usually on her index finger will give these pulses. And what we can do is we can do single pulses. We can vary the amplitude of the pulse, and we could do all type of different frequencies. So in that sense, soft structure is much more versatile than, for example, a vibrotactile motor, because then you always have the buzz of the motor, and you can only use the envelope to play with frequencies. So to slowly wrap up, so the challenges that we have are mainly the wearable actuators, also the multisensory environment. But also more basic things. You think, how hard can it be? But it's like the mapping between the human and the robot movement. Every human is different, and every soft robot is slightly different. So that is something I'll go back to in the next slide, where we can actually add intelligence. And the last question is more a philosophical question, and something that somehow we always expect that haptics is realistic. And of course, if you want to do online shopping and feel like the fabric of your furniture before you buy it, you want it to feel exactly like it will feel in real life. But if you think about training purposes, we could also think about informative information instead of realistic information. So something buzzes or something notifies you that something's going on. Like what's happening on your phone right now. I mean, your phone is not giving you any actual realistic information. It just gives you information about you pushed something or a notification is coming in. So, as I said, not very intelligent yet, but we're getting there. And that's on very different paths, but there are three main paths that I would like to emphasize here. So the first one is what we call embedded intelligence. And that might not be the first thing you think about on an AI summit, but it's think about how structure shapes function, and also how you can use material properties. So think about, if you look at nature again, if you look at a pine cone, it opens when the moisture level in the air is low so that the seeds can go out. But then it closes again if it's much wetter, and it keeps doing that for years. Well, it's already off the tree. So it's something that you cannot actively control within the structure, but it's something that the structure actively controls for you. So second, I already mentioned it slightly, is this machine learning and control. Since every task is slightly different, and also if I grasp something, I mean, there are many different ways to get to the same results. I just need to get it. You can think about adaptive learning, and especially if we have these different robots, because how similar we want to make them. Think about balloons. You can have like one bag of balloons, and they're all fabricated in the same factory, in the same process. But some of them become bigger than others. Some of them have some weak parts, and I think especially with pneumatics or fluidic robots, it will be very difficult to make them all identical. So if you have a smart way of controlling them so that they actually learn to work with their own body, that makes you much more versatile in this world. Another thing is mapping input to desired action. That would be just really fun. I'm not sure whether there's any application for it, but if I would be able to control an elephant trunk remotely, then of course you need to have an interesting mapping between what I want to do and what the robot actually is going to do. And maybe we can think about much cooler things than elephant trunks, like Aquaman kind of things with having 8 more legs and arms. As I said, I don't know what it's useful for, but it could be fun to put in the metaverse. It's always a good solution to everything. And the last one is the sensory information. If you think about how we, as humans or animals, interact with the world, if I send a motor command to my arm, then I also have an afference copy, so I have a prediction of what the outcome would be, and I basically only compare the difference between my expectation of the interaction that's going to happen and the actual interaction that's going to happen. And that is something what is, I think, much more computational efficient than using all sensory information that comes in and that you expect. And I think also from that we can learn something, especially if we have these underactuated flexible structures. So a lot of potential, as I mentioned, but not much data yet. What I would like to point out to you is that we have a national soft robotics consortium. At this moment, we are working on this large perspective grant proposal, working on soft supportive robotics in various different domains. So everyone who's interested in soft robotics, you're very welcome to talk to me to see whether you want to join the consortium, or maybe later on to join at the symposium in May where we can show much more about what we're doing and what the expertise that there is in the Netherlands, because it's actually quite growing. So a little shout out to my team doing all the work, contact details and the website of the Dutch Soft Robotics Consortium. And I would like to thank you for your attention.
Irene, you say very modestly it's actually quite growing. I would say it's actually also quite promising.
Yes.
What you are giving here to us. So again, do not make it smaller than it is. It's great. It's wonderful, and thank you so very much for your bright presentation. That was really very, very insightful. Thank you for that. Yeah, soft robotics. All of a sudden, I see my hands differently than I saw them just 20 minutes before, but that's maybe that's just my problem. Questions? You had one? Yeah, and two. 1, 2, please. 2 gentlemen over there. Just wave, and then my colleague knows to whom. Wonderful.
Thank you very much for your insight. My name is Peter Chu from Thales Enschede. Imagine Elon Musk want to build a center of excellence on Mars for future generation and want to apply remote haptic technique. How do we deal, or what for challenge to deal with latency?
Yes, that's a very, very relevant question. So there are basically 2 solutions that are being investigated. There are probably much more, but there are 2 wide varieties. So one is to have let's say a virtual copy of the world with which you interact, and then that interacts with the environment, so that you actually don't directly have to wait for the delay of the whole communication, but that the delay is being solved in like the virtual part in between. That's one solution. The other solution, which I think is less promising but being used a lot, is like adding all these artificial things like extra damping, which usually destroys your percept. And especially if you go to Mars, like the latency is so big, you can't solve it with just waiting.
Okay. Well, those 2. One more promising than the other one, and for sure there are more. Yeah.
Thank you. My name is Eric. I was wondering, what's the maximum latency that you can afford between the brain sending the motoric command to the hand and the haptic feedback from the complete system on the hand before the brain dissociates?
Yes. So also for that, I would like to give like two types of answers. So the first one is if you really ask people to detect whether there is a discrepancy in time, then it's in the order of a few milliseconds. So most of the haptic devices, if you think about force feedback, they are being rendered at 1,000 hertz, just to be very sure. But because it also depends if you talk about impact. If I hit the table, like it's a very time-specific kind of interaction. Well, if I just do something much more gentle, then it's also much less crucial to have that timing right. The other part of the answer I would like to give here is that humans are also quite flexible. So that's all we have all seen that in visual environments, or having like slight delays in 3D goggles, and so it's much more sensitive on time than the visual domain, but we can still learn to work with it up to maybe tens of milliseconds. Okay. Not go to 100 milliseconds. That will be completely
Okay. Well, thank you so much. Yeah, great question. Thank you so much. It was wonderful having you here. And please, ladies and gentlemen, do not hesitate. If you are not attending the conference Ian was inviting you for in May next year, then maybe you have friends, you have colleagues or whatsoever. So please spread the word.
Yes,
and finally
definitely.
team up. Yeah, great.
Very well.
Thank you so much. Let's have Okay, now I know that there are several program managers from EAISI here in the boardroom. Just stay where you are. Be relaxed, because I'm going to invite Carlo on stage. We will have lunch in a moment, and then I invite you to be back at 1:45, because then the research track continues with more interesting duo talks and insightful information. But we are also anxious to meet and to learn more about the program managers we could rely on. So please, the final word is for you to introduce your program managers.
Thanks, Simone. Important last message before I let you go to the lunch, because you're hungry for probably more knowledge of the people, but also from some food. And that's maybe just a little bit on EAISI and what EAISI is about, and a very important task of EAISI. EAISI, the Eindhoven AI Systems Institute, we started about three and a half years ago. And that was when we as a university also realized, and as a region we realized, that this AI is changing and moving and walking into the front garden of this high-tech industry, these machine builders here in the region. So we thought it was important to step up there. And also, if you tried as a school boy or girl and you wanted to study AI, you landed in all kind of universities on the internet, but not at Eindhoven University. You could not study AI. So we had to step up. That's why we formed EAISI. And it's not a voluntary thing. We set ourselves some very clear targets. So you should be able to study AI in Eindhoven, which is possible already. So after 3.5 years, at least we got that checked. We have now some masters on AI, several masters. You can have the professional education. So if you're already working, we do this together with Jats in the Bosch. You can also have the courses of AI when you're already in the industry. And we're also now working on the bachelor. So that's something that we really stepped up. We also had some money to hire more specialists. Not at our institute, they work together with the institute, but they will work at the faculty, but specific new scientific staff. We already hired 48 of them. Now also to really step up in this AI. Another thing, an important thing and a nice thing is also that we are building our own lab. We hope to open that at the beginning of next year, so we might throw in another party. You will hear about that. And for those who know the Technical University already, it will be placed in the Laplace building. And for old ones like me, that used to be het rekencentrum. So where in the old days we went to with our punch cards even. So Opa vertelt, so we had the punch cards and we had to go there. That was a history lesson. I'm not that old. But also with our floppy disks, because that's where the servers were. And that's where we are going at this moment. We're preparing to build our new lab. So very welcome to also have a look there, if not at the opening. So that's an important thing. We're building this lab and all kind of experiences over there. But actually another very important one is that we also try to step up in the number of research and also get it funded, because that's very important. So today you might be developing some new ideas based on these discussions. We at EAISI are there to help to also make that a program and get it funded, because there's quite some funding on its way, also on a European level and also on national programs. And all modesty, we have some people that are quite well capable of helping you from an idea to make it a project and also to get it funded. And for that, we have quite a small army of project managers. And I just wanted to introduce you to you. And the thing is that Shane, on top of it, he should have been on stage here, but he had already long time ago planned a trip to his family in Australia, and he's still there, and he lands in the end of the week. We initially thought this would be on the 15th of November, so we can't blame him for that, but he's still in Australia. But Shane is the guy to manage it all, but you probably also met him because he's also good in making new projects. So that's Shane to introduce, but I want to shortly introduce these faces, because when you have an idea, and if you're from the university and you have an idea, and this might be an idea, come to us and we might also link you to the industry, because again, we have quite a network over there. And the other way around, if you're from the industry and you say, I have a problem, or I also have an idea and I want to get in contact with the university, again, approach us, because we might also be able to find the right person on the other side. So this is this small army of people that most of them are here, some couldn't go. So and there's also where they specialize in, but if not, they will also always will find somebody else in order to help you with. And just name their names. You can see what their specialism is. And I just asked them to, if they're here, to just shortly wave their hands so they can see that's easy, very friendly, and easy approachable people. So Peter, are you in? Peter is, where's Peter first? Peter, from I knew he could not become. Charlie, I've seen Charlie. Charlie, please stand up. That's Charlie Bastiaanse. A lot of history in Philips and all kind of thing, but also knows his way over there. Hala, I saw you over there. That's Hala Elofai. She's specific on robotics. Hans van Beek over there. Industry and also background in telematics. Margriet van Schijndel. Margriet van Schijndel on mobility, automotive, all that kind of stuff. Hans Driessen, where we have also, I saw him, over there, he's standing in the back, just in time here. Dasha, I saw you as well, in the midst, of course. That's Dasha Alexeva, specializing on health and also doing the links to our sister universities, Utrecht and Wageningen. So it's something that you think, oh, it might so involve some other universities. She's also the person to go to. And Jan Jaap, no, Jan Jaap couldn't come. And maybe, no, we have Jan Jaap here, but you look at this picture, that's, you cannot exchange that with anyone else. That's Jan Jaap. So, these are the people just there to serve you. This is really a good link because we know, and that's why we also organize it as such, the real innovation comes from a combination of different competences, but also to work together with the industry and the university, and they are the natural links. So find them, and they will help you. It comes at a minor cost, and you get a lot of benefits of that. Thank you very much for now, and let's have lunch and let's exchange ideas. Thank you.